so those are the teams that we have organized that are working in this class, and we see only about half of them here.
It's really good. Those prices were those prices that we could get if we wanted to get them online. That's how much they would cost and where to get them at.
Correct.
Okay.
And last year, we had an agreement with HBI, and I don't know whether it's still available, but we were able to get any race car at the BYU price, which was basically half of any of those prices.
That makes sense.
So if you're interested in doing that, just talk to me during the semester, and I'll send an email and try and figure that out. But they were very nice to BYU and gave us basically half off the list price on that.
So just from what I read there, did each university get one of the models?
Yeah, so we have a copy of the model, and the remote team has a copy of the model, and they have the exact same thing. So, okay, so this is intended to be kind of an org chart for a normal company. It's not an org chart for your team, but I do want and need an org chart for your team. There needs to be somebody that's in charge over the entire project. That person is the person that needs to make sure that things are moving down the road. That person probably has a lighter modeling load just because that person's doing all of the organization. So it's kind of a divide and conquer activity that we're working on here. So each team, whether you're just a local team or 3 people local and 3 people remote, you need to come up with what is your organization. Who is your lead modeling person? A person that knows the most about modeling. Who is the person on your team that knows the most about FEA? Who's the person that knows the most about CFD? And you just kind of go through that and you put that person in charge of that particular activity. Does that person do all of the work on that activity? Absolutely not. That person is kind of the gatekeeper for what is turned in by the group. So that person is kind of the quality control person, if you want to think of it that way. Gee, that finite element modeling isn't realistic. The load case, the constraints, the materials, they're just not right. It's not believable. You need to change this and this and this and fix it and do it again. So that's the lead analyst, lead modeler. That person is kind of looking at everything that is being submitted under that kind of area, that kind of topic. Okay? So the question was asked, how much of this do we really model? And if you kind of divide and conquer past last year, I would say most teams got everything modeled. Okay? When you look at the parts list, which you have a booklet, and in the back of it, it gives a parts list. You find out that some of the components are used 20 times. Other components are used 14 times. A few components are used only once. But there's this collection, this list of things, and if you go down through that list and put a name by every one of those parts, you can then get through the modeling of that by the end of the semester. What I would do is, if I'm rusty on CAD modeling, I would start with the simplest parts assigned to me. As I get halfway into the semester, I would then very quickly transition away from the simplest to the most critical. So if there's some part that's buried down deep inside and you're not going to have time to model it, don't model it. And don't talk about it in your final report, because we'll never know that it's not there. Okay? So it's something that you have to pace yourself on. You have to figure out how much of this elephant can our team eat, you know? And initially I would start out, if I'm very uncertain on a particular topic, we're doing topology optimization, I wouldn't pick something that had the ugliest load cases to do my initial topology optimization. I would pick something very simple with a simple load case and get it working. You get halfway into the semester and you rearrange your priorities by saying, wow, if we don't have a chassis that everything hooks to, we're going to be in trouble. Somebody needs to model that. And you just kind of reprioritize where you're going. So if you look at this, you can organize yourself about any of these sub-assemblies. So instead of, I told you, put names on this parts list, we'll do it in a strategic way. The parts list could easily be grouped as the front suspension. And if I do the front left suspension, I just need to mirror it over and it becomes the front right. And on some of these cars, the front suspension is so close to the rear suspension, you probably want to assign that to the same individual or the same group of individuals, okay? So by looking at this book that we've handed out, you can kind of begin to say who's over what, element or piece of it. Okay? And so this is kind of looking at it from a suspension standpoint. We could also look at it, if we wanted to get kind of organized around the chassis. Well, on most of these books, the chassis components kind of all run down the center of the thing. And you can begin saying, we need a chassis group, we need a suspension group, we need a powertrain group. You can basically kind of think about organizing yourselves functionally by what kind of module that you're working on. Last semester, I don't think any of the teams got to the electrical part. Okay? It would be interesting to see some of the electrical model this semester. The wiring is not impossible. The CAD systems allow you to represent that kind of objects. And so you may want to think about somebody that's doing the electrical system. All of you, in some way, shape, or form, will be your own body group. Right? So you need to each kind of be thinking about, well, I have to model some kind of a body. Last semester, a year ago, there were some bodies that were very boxy, okay? Very square, very simple to model and cut shapes out of, and there were some that were very stylized, okay? And you have to just kind of say, where am I at modeling? If you're very good at surface modeling, then you want to push yourself and get something that's really stylized. If you're struggling modeling surfaces, then start really simple, boxy or whatever, and we have tutorials, we have lab exercises that will walk you through this kind of stuff. You got a question?
Yeah, on that picture, there's 4 contact points with the chassis.
Yep.
Does our body design have to touch those 4 contact points or modify something?
If you get together as a team and decide to modify that, you can. In the past, they've always kind of just left those as 4 contact points that everybody's going to let sit on them. Now, most of these have posts, and the posts can go up and down. So you can move the cotter key up or cotter key down kind of thing to lock it to a different height, so you can raise and lower it. But those 4 points were kind of locked in past semesters. So here's a little functional organization chart where they've kind of listed team members 1 to 6, and they've listed out all of the different activities that we go through in the project booklet. So the project booklet has assemblies, it has topology, it has data transfer, it has wire, and they just kind of went through there and said, who's going to be kind of the lead, who's going to be in charge, who's going to be kind of the assistant or the backup, and they assigned it out that way. It's just an approach on getting organized. You don't have to copy this, you can organize yourself any way that you want. It's just one example. After you get organized, what we want you to do is come up with a schedule. so that you can basically work to that. You looked at the number of parts, you say we've got 150 parts that have to be generated, you divide that by 6, you figure out kind of a timetable, and you set a timetable that each team member is going to kind of march to. And that way you can kind of map your progress. Okay? So you have in your hands now the project. It's time to get your team organized. It's time to set a schedule that you're going to try and follow. It's time that you begin doing intense collaboration with your team members. From this point on, we will take labs and we will do topology optimization. We will do top-down assembly skeleton exercise. We will do a motion exercise. We will do a mass property. And so we will be covering these things as we march down through the system, and your timetable ought to reflect when you're going to be learning some of this information. So I'm going to have all the parts modeled and ready for doing mass properties on this date, because this is when we start talking about mass properties. Okay? So you've got the calendars, you've got the schedules, and you can begin looking at that. So the last thing that we're going to talk today about are what BYU calls culture grams. Have any of you ever, here at BYU, ever heard of BYU culture grams? Okay, a couple of you. The university a few years ago kind of developed a 3-page, 5-page description of what one would need to know if they were traveling to a country or trying to do work in a country. And so we have uploaded to TCC culture grams for each of the different locations that you're linked up with. So there is a Canadian culture gram, there's one for China, there's one for Korea, there's one for Mexico, Brazil, one for Taiwan. They're loaded up on TCC. If you are interacting with somebody from China, we would ask that you would read the culture gram so that you can better appreciate and understand that country. We would ask that your team members in China read the US culture gram, which is also loaded up on TCC. And that is part of the collaboration exercises that you are working on. Lab 1, 2, 3 are dealing with trying to get so that you're comfortable with each of these cultures, these countries that you're interacting with. So here's an example of one for Mexico. It goes on for a few pages, okay? And it talks about lifestyle, it talks about food, it talks about their monetary system, it talks about a lot of just good information to kind of be aware of when you're working with them. Any questions?